Alcohols, phenols, and ethers. Alcohols, phenols, and ethers are the basic compounds for the formation of detergents, antiseptics, and fragrances, respectively. Substitution of one or more hydrogen atoms from a hydrocarbon by another atom or a group of atoms results in the formation of an entirely new compound having altogether different properties and applications. Alcohols and phenols are formed when a hydrogen atom in a hydrocarbon, aliphatic and aromatic respectively, is replaced by -OH group. These classes of compounds find wide applications in industry as well as in day-to-day life. For instance, have you ever noticed that ordinary spirit used for polishing wooden furniture is chiefly a compound containing hydroxyl group ethanol? The sugar we eat, the cotton used for fabrics, the paper we use for writing are all made up of compounds containing -OH groups. Just think of life without paper. No notebooks, books, newspapers, currency notes, checks, certificates, etc. The magazines carrying beautiful photographs and interesting stories would disappear from our life. It would have been really a different world. An alcohol contains one or more hydroxyl, that is OH groups, directly attached to carbon atoms. Of an aliphatic system, that is CH3OH, while a phenol contains -OH groups directly attached to carbon atoms of an aromatic system, that is C6H5OH. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy and aryloxy group, that is RO or ARO, yields another class of compounds known as ethers. For example, CH3OCH3, that is dimethyl ether. You may also visualize ethers as compounds formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this unit, we shall discuss the chemistry of three classes of compounds, namely alcohols, phenols, and ethers. Classification. The classification of compounds makes their study systematic and hence simpler. Therefore, let us first learn how are alcohols, phenols, and ethers classified. Alcohols: mono, di, tri, or polyhydric alcohols. Alcohols and phenols may be classified as mono, di, tri, or polyhydric compounds depending on whether they contain 1, 2, 3, or many hydroxyl groups respectively in the structures as given below. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. Number 1. Compounds containing CsP3 -OH bond. In this class of alcohols, the -OH group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified as follows: primary, secondary, and tertiary alcohols. In these three types of alcohols, the -OH group is attached to primary, secondary, and tertiary carbon atom, respectively, as depicted below. Allylic alcohols. In these alcohols, the -OH group is attached to a sp3 hybridized carbon adjacent to the carbon-carbon double bond, that is to an allylic carbon. For example, benzylic alcohols. In these alcohols, the -OH group is attached to a sp3 hybridized carbon atom next to an aromatic ring. For example, allylic and benzylic alcohols may be primary, secondary, or tertiary. Number 2. Compounds containing CsP2 -OH bond. These alcohols contain -OH group bonded to a carbon-carbon double bond, that is, to a vinylic carbon or to an aryl carbon. These alcohols are also known as vinylic alcohols. Vinylic alcohols: CH2 double bond CH-OH. Phenols: mono, di, and trihydric phenols. Ethers. Ethers are classified as simple or symmetrical. If the alkyl or aryl groups attached to the oxygen atom are the same, and mixed or unsymmetrical if the two groups are different. Diethyl ether C2H5OC2H5 is symmetrical ether, whereas C2H5OCH3 and C2H5OC6H5 are unsymmetrical ethers. Nomenclature. A. Alcohols. The common name of an alcohol is derived from the common name of the alkyl group and adding the word alcohol to it. For example, CH3OH is methyl alcohol. According to IUPAC system, the name of an alcohol is derived from the name of the alkane from which the alcohol is derived by substituting E of alkane with the suffix OL. The position of substituents are indicated by numerals. For these, the longest carbon chain, that is parent chain, is numbered starting at the end nearest to the hydroxyl group. The positions of the -OH group and other substituents are indicated by using the numbers of carbon atoms to which these are attached. For naming polyhydric alcohols, the E of alkane is retained and the ending OL is added. The number of -OH groups is indicated by adding the multiplicative prefix di, tri, etc. before OL. The position of -OH groups are indicated by appropriate locands. For example, OH CH2CH2OH is named as ethane 1,2-diol. Table gives common and IUPAC names of a few alcohols as examples. Table: common and IUPAC names of some alcohols. Compound: common name, IUPAC name. CH3OH, methyl alcohol, methanol. CH3CH2CH2OH, N-propyl alcohol, propan-1-ol. CH3CHOH CH3, isopropyl alcohol, propan-2-ol. CH3CH2CH2CH2OH, N-butyl alcohol, butan-1-ol. CH3CHOH CH2CH3, secondary butyl alcohol, butan-2-ol. CH3CH CH2OH, isobutyl alcohol, 2-methylpropan-1-ol. CH3C CH3CH3OH, tertiary butyl alcohol, 2-methylpropan-2-ol. OHCH2CH2OH, ethylene glycol, ethane 1,2-diol. CH2OH CHOH CH2OH, glycerol, propan 1,2,3-triol. Cyclic alcohols are named using the prefix cyclo and considering the -OH group attached to C1. B. Phenols. The simplest hydroxy derivative of benzene is phenol. It is its common name and also an accepted IUPAC name. As structure of phenol involves a benzene ring, in its substituted compounds the terms ortho 1,2 disubstituted, meta 1,3 disubstituted, and para 1,4 disubstituted are often used in the common names. Dihydroxy derivatives of benzene are known as 1,2, 1,3 and 1,4 benzene diol. C. Ethers. Common names of ethers are derived from the names of alkyl aryl groups written as separate words in alphabetical order and adding the word ether at the end. For example, CH3OC2H5 is ethyl methyl ether. Table: common and IUPAC names of some ethers. Compound: common name, IUPAC name. CH3OCH3 dimethyl ether, methoxymethane. C2H5O C2H5 diethyl ether, ethoxyethane. CH3OCH2CH2CH3 methyl N-propyl ether, 1-methoxypropan. C6H5OCH3 methyl phenyl ether, anisole, methoxybenzene, anisole. C6H5O CH2CH3 ethyl phenyl ether, phenetol, ethoxybenzene. C6H5O CH26CH3 heptyl phenyl ether, 1-phenoxyheptane. CH3O CH3CH3 methyl isopropyl ether 2-methoxypropane, C6H5O CH2CH2 CH3CH3, phenyl isopentyl ether 3-methyl-butoxybenzene, CH3O CH2 CH2O CH3 1,2-diethoxyethane, CH3CH3OC2H5 2-ethoxy 1,1-dimethyl cyclohexane. If both the alkyl groups are the same, the prefix di is added before the alkyl group. For example, C2H5OC2H5 is diethyl ether. According to IUPAC system of nomenclature, ethers are regarded as hydrocarbon derivatives in which a hydrogen atom is replaced by an OR or OAR group, where R and AR represent alkyl and aryl groups respectively. The larger R group is chosen as the parent hydrocarbon. The names of a few ethers are given as example in table. Example: give IUPAC names of the following compounds. Solution: 1. 4-chloro 2,3-dimethylpentane 1-ol 2. 2-ethoxypropane 3. 2,6-dimethylphenol 4. 1-ethoxy 2-nitrocyclohexane. Structures of functional groups. In alcohols, the oxygen of the -OH group is attached to carbon by a sigma bond formed by the overlap of a sp3 hybridized orbital of carbon with a sp3 hybridized orbital of oxygen. Figure depicts structural aspects of methanol, phenol, and methoxymethane. The bond angle COH in alcohols is slightly less than the tetrahedral angle, that is 109 degree 28 minute. It is due to the repulsion between the unshared electron pairs of oxygen. In phenols, the -OH group is attached to sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length, that is 136 parameter, in phenol is slightly less than that in methanol. This is due to number 1. Partial double bond character on account of the conjunction of unshared electron pair of oxygen with the aromatic ring. Section 4 and number 2. sp2 hybridized state of carbon to which oxygen is attached. In ethers, the 4 electron pairs, that is, the 2 bond pairs and 2 lone pairs of electrons on oxygen, are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the two bulky -R groups. The CO bond length, 141 parameter, is almost the same as in alcohols. Alcohols and phenols. Preparation of alcohols. 1. From alkenes. 1. By acid catalyst hydration. Alkenes react with water in the presence of acid as catalyst to form alcohols. In case of unsymmetrical alkanes, the conditioned reaction takes place in accordance with Markovnikov's rule. Mechanism. The mechanism of the reaction involves the following 3 steps. Step 1. Protonation of alkene to form carbocation by electrophilic attack of H3O+. H2O plus H plus gives H3O+. Step 2. Nucleophilic attack of water on carbocation. Step 3. Deprotonation to form an alcohol. Number 2. Bihydroboration oxidation. Diborane, that is BH3 twice, reacts with alkenes to give trialkyl boranes as addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. CH3CH double bond CH2 plus HBH2 twice gives CH3CHH CH2BH2. In the presence of CH3CH double bond CH2 gives CH3CH2CH2 twice BH. In the presence of CH3CH double bond CH2 gives CH3CH2CH23B in the presence of 3H2O2 minus OH H2O gives 3CH3CH2CH2OH propane 1-ol plus BOH3. The addition of boron to the double bond takes place in such a manner that boron atom gets attached to the sp2 carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in a way opposite to the Markov-Nikov's rule. In this reaction, alcohol is obtained in excellent yield. Number 2. From carbonyl compounds. 1. By reduction of aldehydes and ketones. Aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalysts, that is, catalytic hydrogenation. The usual catalyst is a finely divided metal such as platinum, palladium, or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydrate, that is NaBH4, or lithium aluminium hydrate, that is LiAlH4. Aldehydes yield primary alcohols, whereas ketones give secondary alcohols. RCHO plus H2 in the presence PD gives RCH2OH. RCOR- in the presence of NaBH4 gives RCHOH-R-. 2. By the reduction of carboxylic acids and esters. Carboxylic acids are reduced to primary alcohols in excellent yields by lithium aluminium hydride, a strong reducing agent. RCOOH in the presence of 1 LiAlH4, 2 H2O gives RCH2OH. However, LiAlH4 is an expensive reagent and therefore used for preparing special chemicals only. Commercially, acids are reduced to alcohols by converting them to the esters, that is section 4.4, followed by their reduction using hydrogen in the presence of catalyst, that is catalytic hydrogenation. RCOOH in the presence of R-OH H plus gives RCOOR. In the presence of H2 catalyst gives RCH2OH plus R-OH. Number 3. From Grignard reagents. Alcohols are produced by the reaction of Grignard reagents with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of the adduct yields an alcohol. The overall reactions using different aldehydes and ketones are as follows. HCHO plus RMGX gives RCH2O-MgX in the presence of H2O gives RCH2OH plus MgOHX. RCHO plus R-MgX gives RCHR-OMgX in the presence of H2O gives RCHR-OH plus MgOHX. RCOR plus R-MgX gives RCR-OMgX in the presence of H2O, RCR-OH plus MgOHX. You will notice that the reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehydes, and tertiary alcohol with ketones. Example: give the structures and IUPAC names of the products expected from the following reactions. A. Catalytic reduction of butanol. B. Hydration of propane in the presence of dilute sulfuric acid. C. Reaction of propanone with methyl magnesium bromide followed by hydrolysis. Solution: ACH3CH2CH2OH butan 1-ol, B. CH3CHOH CH3 propane 2-ol, C. CH3CCH3CH3OH 2-methyl propane 2-ol. Preparation of phenols. Phenol, also known as carbolic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivatives by any of the following methods. Number 1. From haloarenes. Chlorobenzene is fused with NaOH at 623 Kelvin and 323 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide, so produced. Number 2. From benzene sulfonic acid. Benzene is sulfonated with oleum and benzene. Sulfonic acid so formed is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of the sodium salt gives phenol. Number 3. From diazonium salts. A diazonium salt is formed by treating an aromatic primary amine with nitrous acid, that is NaNO2 plus HCl, at 273 to 278 Kelvin. Diazonium salts are hydrolyzed to phenols by warming with water or by treating with dilute acids. Number 4. From cumin. Phenol is manufactured from the hydrocarbon cumin. Cumin, that is isopropylbenzene, is oxidized in the presence of air to cumin hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. Physical properties. Alcohols and phenols consist of two parts, an alkyl aryl group and a hydroxyl group. The properties of alcohols and phenols are chiefly due to the hydroxyl group. The nature of alkyl and aryl groups simply modify these properties. Boiling points. The boiling points of alcohols and phenols increase with increase in the number of carbon atoms, that is, increase in van der Waals forces. In alcohols, the boiling points decrease with increase of branching in carbon chain, that is, because of decrease in van der Waals forces with decrease in surface area. The -OH group in alcohols and phenols is involved in intermolecular hydrogen bonding as shown below. Boiling points of alcohols and phenols are higher in comparison to other classes of compounds, namely hydrocarbons, ethers, haloalkanes, and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling points differ widely. The boiling point of methoxymethane is intermediate of the two boiling points. The high boiling points of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbons. Solubility. Solubility of alcohols and phenols in water is due to their ability to form hydrogen bonds with water molecules as shown. The solubility decreases with increase in size of alkyl aryl, that is hydrophobic groups. Several of the lower molecular mass alcohols are miscible with water in all proportions. Example: arrange the following sets of compounds in order of their increased boiling points. A. Pentane 1-ol, butane 1-ol, butane 2-ol, ethanol, propane 1-ol, methanol. B. Pentane 1-ol, N-butane, pentanal, ethoxyethane. Solution: A. Methanol, ethanol, propane 1-ol, butane 2-ol, butane 1-ol, pentane 1-ol. B. N-butane, ethoxyethane, pentanal and pentane 1-ol. Chemical reactions. Alcohols are versatile compounds. They react both as nucleophiles and electrophiles. The bond between OH is broken when alcohols react as nucleophiles. Alcohols as nucleophiles. 1. ROH plus C gives ROHC gives ROC plus H plus. Number 2. The bond between CO is broken when they react as electrophils. Protonated alcohols react in this manner. Protonated alcohols as electrophils. RCH2OH plus H plus gives RCH2OH2 plus Br minus plus CH2R. OH2 plus gives BrCH2R plus H2O. Based on the cleavage of OH and CO bonds, the reactions of alcohols and phenols may be divided into two groups. A. Reactions involving cleavage of OH bond. Number 1. Acidity of alcohols and phenols. Number 1. Reaction with metals. Alcohols and phenols react with active metals such as sodium, potassium, and aluminium to yield corresponding alkoxides or phenoxides and hydrogen. In addition to this, phenols react with aqueous sodium hydroxide to form sodium phenoxides. The above reactions show that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are Bronsted acids, that is, they can donate a proton to a stronger base. B minus base plus HOR acid gives BH conjugate acid plus OR conjugate base. Number 2. Acidity of alcohols. The acidic character of alcohols is due to the polar nature of OH bond. An electron releasing group, that is CH3C2H5, increases electron density on oxygen, tending to decrease the polarity of OH bond. This decreases the acid strength. For this reason, the acid strength of alcohols decreases in the following order. Alcohols are, however, weaker acids than water. This can be illustrated by the reaction of water with an alkoxide. RO base plus HOH acid gives ROH conjugate acid plus OH conjugate base. This reaction shows that water is a better proton donor, that is, stronger acid, than alcohol. Also, in the above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxides are stronger bases. That is, sodium ethoxide is a stronger base than sodium hydroxide. Alcohols act as Bronsted bases as well. It is due to the presence of unshared electron pairs on oxygen, which makes them proton acceptors. Number 3. Acidity of phenols. The reactions of phenol with metals, that is, for example, sodium aluminium and sodium hydroxide, indicate its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule, as depicted in its resonance structures, causes the oxygen of -OH group to be positive. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acids than alcohols and water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than the one in which hydroxyl group is attached to an alkyl group. Due to the higher electronegativity of sp2 hybridized carbon of phenol, to which -OH is attached, electron density decreases on oxygen. This increases the polarity of OH bond and results in an increase in ionization of phenols than that of alcohols. Now let us examine the stabilities of alkoxide and phenoxide ions. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge, that is, structures 1,5, makes phenoxide ion more stable and favors the ionization of phenol. Although there is also charge delocalization in phenol, Its resonance structures have charge separation due to which the phenol molecule is less stable than phenoxide ion. In substituent phenols, the presence of electron withdrawing groups such as nitro groups enhances the acidic strength of phenol. This effect is more pronounced when such a group is present at ortho and para positions. It is due to the effective delocalization of negative charge in phenoxide ion when substituent is at ortho or para position. On the other hand, electron-releasing groups, such as alkyl groups in general, do not favor the formation of phenoxide ion, resulting in decrease in acid strength. Crasols, for example, are less acidic than phenol. Table: pKa values of some phenols and ethanol. Compound formula: pKa. Orthonitrophenol, ortho NO2C6H4OH 7.2. Metanitrophenol, meta NO2C6H4OH 8.3. Paranitrophenol, para NO2C6H4OH 7.1. Phenol C6H5OH 10. Orthocrasol, ortho CH3C6H4OH 10.2. Metacrasol, MCH3C6H4OH 10.1. Paracrasol, para CH3C6H4OH 10.2. Ethanol, C2H5OH 15.9. Example: arrange the following compounds in increasing order of their acid strength: propan-1-ol, 2,4,6-trinitrophenol, 3-nitrophenol, 3,5-dinitrophenol, phenol, 4-methylphenol. Solution: propan-1-ol, 4-methylphenol, phenol, 3-nitrophenol, 3,5-dinitrophenol, 2,4,6-trinitrophenol. 2. Esterification. Alcohols and phenols react with carboxylic acids, acid chlorides and acid anhydrides to form esters. Ar or ROH plus R-COOH, H plus reversible, Ar/ROCOR plus H2O. Ar or ROH plus R-CO twice O, H plus reversible, Ar or ROCOR plus R-COOH. R or AROH plus R-COCl pyridine gives R or AROCOR plus HCl. The reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible, and therefore water is removed as soon as it is formed. The reaction with acid chloride is carried out in the presence of a base, that is pyridine, so as to neutralize HCl which is formed during the reaction. It shifts the equilibrium to the right hand side. The introduction of acetyl, that is CH3CO group in alcohols or phenols, is known as acetylation. Acetylation of salicylic acid produces aspirin. B. Reactions involving cleavage of carbon-oxygen CO bond in alcohols. The reactions involving cleavage of CO bond take place only in alcohols. Phenols show this type of reaction only with zinc. 1. Reaction with hydrogen halides. Alcohols react with hydrogen halides to form alkyl halides. ROH plus HX gives RX plus H2O. The difference in reactivity of three classes of alcohols with HCl distinguishes them from one another, that is, Lucas test. Alcohols are soluble in Lucas reagent, that is, concentrated HCl and ZnCl2, while their halides are immiscible and produce turbidity in solution. A tertiary alcohol's turbidity is produced immediately as they form the halides easily. Primary alcohols do not produce turbidity at room temperature. 2. Reaction with phosphorus trihalides. Alcohols are converted to alkyl bromides by reaction with phosphorus tribromide. 3. Dehydration. Alcohols undergo dehydration, that is, removal of a molecule of water, to form alkenes on treating with a protic acid, for example, concentrated H2SO4 or H3PO4, or catalysts such as anhydrous zinc chloride or alumina. CHCOH H plus heat gives C double bond C plus H2O. Ethanol undergoes dehydration by heating it with concentrated H2SO4 at 443 Kelvin. C2H5OH H2SO4 443 Kelvin gives CH2 double bond CH2 plus H2O. Secondary and tertiary alcohols are dehydrated under milder conditions. For example, CH3CHOH-CH3 in the presence of 85% 3PO4 440 Kelvin gives CH3CH double bond CH2 plus H2O. CH3CCH3CH3OH in the presence of 20% H3PO4 358 Kelvin gives CH3C double bond CH2 CH3 plus H2O. Thus, the relative ease of dehydration of alcohols follows the following order. Tertiary is greater than secondary is greater than primary. The mechanism of dehydration of ethanol involves the following steps. Mechanism. Step 1. Formation of protonated alcohol. Step 2. Formation of carbocation. It is the slowest step and hence the rate determining steps of the reaction. Step 3. Formation of ethane by elimination of a proton. The acid used in step 1 is released in step 3. To drive the equilibrium to the right, ethane is removed as it is formed. 4. Oxidation. Oxidation of alcohols involves the formation of a carbon-oxygen double bond with cleavage of an OH and CH bonds. HCOH gives C double bond O. Such a cleavage and formation of bonds occur in oxidation reactions. These are also known as dehydrogenation reactions, as this involve loss of dihydrogen from an alcohol molecule. Depending on the oxidizing agent used, a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. RCH2OH gives RCH double bond O gives RCOH double bond O. Strong oxidizing agents such as acidified potassium permanganate are used for getting carboxylic acids from alcohols directly. CrO3 in anhydrous medium is used as the oxidizing agent for the isolation of aldehydes. RCH2OH CrO3 gives RCHO. A better reagent for oxidation of primary alcohols to aldehydes in good yield is pyridinium chlorochromate, that is PCC, a complex of chromium trioxide with pyridine and HCl. CH3CH double bond CH CH2OH. PCC gives CH3CH double bond CH CHO. Secondary alcohols are oxidized to ketones by chromic anhydride, that is CrO3. RCHOH R- gives RC double bond O R-. Tertiary alcohols do not undergo oxidation reaction. Under strong reaction conditions such as strong oxidizing agents, that is KMnO4, and elevated temperatures, cleavage of various CC bonds takes place and a mixture of carboxylic acids containing lesser number of carbon atoms is formed. When the vapors of a primary or secondary alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and an aldehyde or a ketone is formed, while tertiary alcohols undergo dehydration. C. Reactions of phenols. Following reactions are shown by phenols only. 1. Electrophilic aromatic substitution. In phenols, the reactions that take place on the aromatic ring are electrophilic substitution reactions. The OH group attached to the benzene ring activates it towards electrophilic substitution. Also, it directs the incoming group to ortho and para positions in the ring as these positions become electron-rich due to the resonance effect caused by OH group. The resonance structures are shown under acidity of phenols. Common electrophilic aromatic substitution reactions taking place in phenol are as follows. 1. Nitration. With dilute nitric acid at low temperature, that is 298 Kelvin, phenol yields a mixture of ortho and para nitrophenols. The ortho and para isomers can be separated by steam distillation. Orthonitrophenol is steam volatile due to intramolecular hydrogen bonding, while para-nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as picric acid. The yield of the reaction product is poor. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it to phenol 2,4-disulfonic acid, and then with concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the question of the reactions involved? 2. Halogenation. On treating phenol with bromine, different reaction products are formed under different experimental conditions. A. When the reaction is carried out in solvents of low polarity such as CHCl3 or CS2 and at low temperature, monobromophenols are formed. The usual halogenation of benzene takes place in the presence of a Lewis acid such as FeBr3, which polarizes the halogen molecule in case of phenol. The polarization of bromine molecule takes place even in the absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring. B. When phenol is treated with bromine water, 2,4,6-tribromophenol is formed as white precipitate. Example: write the structure of the major products expected from the following reactions. A. Mononitration of 3-methylphenol. B. Dinitration of 3-methylphenol. C. Mononitration of phenylmethanoate. Solution: the combined influence of OH and CH3 groups determine the position of the incoming group. 2. Kolbe's reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Orthohydroxybenzoic acid is formed as the main reaction product. 3. Reimer-Tiemann reaction. On treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring. This reaction is known as Reimer-Tiemann reaction. The intermediate substituted benzyl chloride is hydrolyzed in the presence of alkali to produce salicylic aldehyde. 4. Reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. 5. Oxidation. Oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone. In the presence of air, phenols are slowly oxidized to dark-colored mixtures containing quinones. Some commercially important alcohols. Methanol and ethanol are among the two commercially important alcohols. 1. Methanol. Methanol, CH3OH, also known as wood spirit, was produced by destructive distillation of wood. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature, and in the presence of ZNO Cr2O3 catalyst CO plus 2H2 in the presence of ZNO Cr2O3 200 to 380 M 573 Kelvin to 673 Kelvin gives CH3OH. 2. Ethanol. Ethanol C2H5OH is obtained commercially by fermentation. The oldest method is from sugars. The sugar is molasses, sugarcane or fruits such as grapes is converted to glucose and fructose, that is both of which have the formula C6H12O6 in the presence of an enzyme invertase. Glucose and fructose undergo fermentation in the presence of another enzyme, zymase, which is found in yeast. C12H22O11 plus H2O gives C6H12O6 plus C6H12O6. C6H12O6 gives 2C2H5OH plus 2CO2. In winemaking, grapes are the source of sugars and yeast. As grapes ripen, the quantity of sugar increases and yeast grows on the outer skin. When grapes are crushed, sugar and the enzyme come in contact and fermentation starts. Fermentation takes place in anaerobic conditions, that is, in absence of air. Carbon dioxide is released during fermentation. The action of zymase is inhibited once the percentage of alcohol formed exceeds 14%. If air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. Ethanol is a colorless liquid with boiling point 351 Kelvin. It is used as a solvent in paint industry and in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate, that is, to give it a color, and pyridine, that is, a foul-smelling liquid. It is known as denaturation of alcohol. Nowadays, large quantities of ethanol are obtained by hydration of ethane, that is, section 4. Preparation of ethers. 1. By dehydration of alcohols. Alcohols undergo dehydration in the presence of protic acids, that is H2SO4, H3PO4. The formation of the reaction product, alkene or ether, depends on the reaction conditions. For example, ethanol is dehydrated to ethane in the presence of sulfuric acid at 443 Kelvin. At 413 Kelvin, ethoxyethane is the main product. CH3CH2OH in the presence of H2SO4, 443 Kelvin, CH2 double bond CH2. CH3CH2OH in the presence of H2SO4, 413 Kelvin, C2H5O C2H5. The formation of ether is a nucleophilic bimolecular reaction, that is SN2, involving the attack of alcohol molecule on a protonated alcohol as indicated below. 1. CH3CH2OH plus H plus gives CH3CH2OHH. 2. CH3CH2OH plus CH3CH2OHH gives CH3CH2O plus H CH2CH3 plus H2O. 3. CH3CH2O plus H CH2CH3 gives CH3CH2OCH2CH3 plus H plus. Acidic dehydration of alcohols. To give an alkene is also associated with substitution reaction to give an ether. The method is suitable for the preparation of ethers having primary alkyl groups only. The alkyl group should be unhindered and the temperature be kept low. Otherwise, the reaction favors the formation of alkene. The reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in higher classes. However, the dehydration of secondary and tertiary alcohols to give corresponding ethers is unsuccessful as elimination competes over substitution, and as a consequence, alkenes are easily formed. Can you explain why is bimolecular dehydration not appropriate for the preparation of ethyl-methyl ether? 2. Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide. Rx plus R-O minus Na plus gives ROR plus NaX. Ethers containing substituted alkyl groups, that is, secondary or tertiary, may also be prepared by this method. The reaction involves SN2 attack of an alkoxide ion on primary alkyl halide. CH3CCH3CH3O minus Na plus CH3Br gives CH3O CCH3CH3CH3 plus NaBr. Better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3ONa with CH33CBr gives exclusively 2-methylpropane. CH3CCH3CH3Br plus Na plus O minus CH3 gives CH3CCH3 double bond CH2 plus NaBr plus CH3OH. It is because alkoxides are not only nucleophiles but strong bases as well. They react with alkyl halides leading to elimination reactions. Example: the following is not an appropriate reaction for the preparation of tertiary butyl ethyl ether. 1. What would be the major product of this reaction? 2. Write a suitable reaction for the preparation of tertiary butyl ethyl ether. Solution: 1. The major product of the given reaction is 2-methylprop-1-ene. It is because sodium ethoxide is a strong nucleophile as well as a strong base. Thus, elimination reaction predominates over substitution. CH3CCH3CH3O minus Na plus CH3CH2Cl gives CH3CCH3CH3OC2H5. Phenols are also converted to ethers by this method. In this, phenol is used as the phenoxide moiety.